we call it variable speed wind turbine with full scale power converter. So this kind of the power converter is normally equipped with these synchronized or asynchronized generators. Normally, we can use this permanent magnet synchronized generator as an example. So here we can see that since this back-to-back power converter is connected to the stator side of this generator, so we can eliminate this slip rings that is normally very fragile due to the wear out issues. And here we can see that we can also have the possibilities to reduce this gearbox if this pole of this generator is we have enough pole pairs of this generator. Then we can also have this concept as a gearless concept. And another good thing for this configuration is that here, since these DC-link capacitors can fully decouple the generator side control and the grid side control. So here, actually, if some fault happens at these conditions, so these grid side converters can have the full controllabilities to control the active power and red power at different kind of the sequence frame. Yeah. And if we take a look at the grid code requirements from the modern world, we could see that it can be divided into the two kinds. First kind is that during normal operations, and second category could be that if some voltage disturbance happens. And in case of these normal operations, we could see that if the grid frequency become higher, and normally we need to reduce the power that is generated from the wind turbine. And here, so we can find out the relationship between the grid frequency and also the active power. And another thing is that these wind turbines also need to have the abilities to provide or absorb this rated power. So here we can see if this curve is coming from a German grid code, and we can see that if the active power is above 20%, we need to provide up to 40% of this overexcited rated power and 30% of this underexcited rated power in this case. And these are some conditions under this normal case. And if some fault happens, then we have also the different profiles that we need to fulfill to meet the grid codes. So here, for example, in case of this low voltage rise-through conditions, so we can see that also. This is a curve from this German grid code, and here we can see that even the grid voltage becomes zero, then the wind turbine system still need to withstand this kind of the grid faults for around 150 milliseconds. And here we can see that if the grid fault is not that severe, then we can see that the standard withstand time of this grid fault will also become longer. And this is the case for the low voltage rise-through. And in case of the high voltage rise-through, and we can see that the wind turbine need to withstand up to 20% more of this grid voltage. And we could also see that the withstand time of these wind turbines at the different voltage levels in case of the high voltage could be different in this profile. And meanwhile, in case of this low voltage rise-through, then the wind turbine need to provide some rated power, try to support this grid voltage recovery. So here we can see that if the dip level is higher than 0.5, then we could see that up to 1 pu rated power need to be, or rated current is need to be injected to the power system. And similarly, in case of the high voltage, then the wind turbine need to absorb some rated power. And here we could also see the relationship between the different grid voltage and also this underexcited rated power that's needed from the wind turbine system. Yeah. And if we take a look at the general control structure of the modern wind turbine system. So as we mentioned before, different manufacturers may have their different preference of this general type. So here, for example, you can have this Dfid induction generator, or this permanent magnet synchronous generator, or also this normal induction generator. But regardless of this topage of these generators, we all have these back-to-back power converters before we connect to the power grid. And from the low level to high level, generally speaking, we can divide them into the 3 categories. So first one is that we call it this power converter control level. So in this level, the key targets of this control is we try to control the voltage or current from the stator side or the generator side. And meanwhile, we also need to do some grid synchronizations to have this active power or reactive power that is synchronized to the power grid. And this is a level 1. And in case of the level 2, we call it wind turbine control strategies. And here in this level of the control, we need to do some power maximization, like MPPT control, or some fault right-through operations, or or also some grid support functions if the grid is not in a normal condition. And the highest level is that we call it this grid integration control. And here the output of this control system will depend on what is the commands from the TSO, or we will also need to consider what is the current conditions of the power grid, like the frequency and the amplitude of this power grid. Now we need to provide some active or reactive power reference according to this TSO or the current conditions of this power grid. So here in these lectures, we are mainly focused on the first 2 levels, like power converter control and also the wind turbine control. Yeah. So now we will try to see what is how we can model and control these wind turbine systems. So here we only focus on the type 3 or type 4 wind turbine system. We call it the Dfid induction generator, or this PM, or we call it the PMSD system. And then we will try to see how we can control them in terms of the grid side converter, and then we will try to see how we can model and control for the other side of the power converter, that is the machine side power converters. So if we take a look at this general configuration of this system, now here we can see that for these Dfid systems, is just equipped with this partial scale power converter. And as we mentioned before, that there's an advantage that we have this cost-effective power converter. And the main drawback is that we need to use a crowbar, or we also have these slip rings, because this power converter is connected to the rotor of this Dfid. And if we take a look at these PMSD systems, now we can see that there are 2 key advantages for this configuration. First one is that we can also try to eliminate this fragile part of this gearbox. And another thing is that since this back-to-back power converter is fully decoupled from each other, now we can have the more controllabilities to control the power converters in case of the grid faults, for example. But here we can see that the rating of this back-to-back power converter is much higher compared to this partial scale power converter. So maybe from the cost perspective, it will become more expensive for this full-scale power converter. Yeah. And if we take a more detailed look at this control target for this Dfid induction generator system, now we can see that here are some overall control structures we have. And here we can see that for the load side converters, the key objective of this control is that we try to control the stator side active power and reactive power through this DQ transformation of this generator. And here we need to see that we need to censor this a lot of informations before we do the control, like this load speed and also the stator and the stator side current and voltage, and also the load voltage we needed to do the control. And for the grid side converters, and here we can see that the control objective of this grid side converter is first is that we try to keep these DC voltages fixed, and another thing is that we need to provide some red power if needed by the power grid. So here is the key control targets for this DFID system. And if we take a look at this PMSG systems, then here we can see that for the machine side converters, and here we can see that we will need to control the active power and red power, that is from the PMSG. And for the grid side converters, we can see that the control objective is actually the same. First is that we need to control the DC voltage. And the second thing is that we also need to provide or absorb some red power if power grid have some requirements. So generally speaking, we can see that regardless of this DFID or PMSG system, the control objective from the grid side converters are the same, because we need to control the red power and also this DC voltage. So here we try to start with the control and the modeling of the grid side converters first. Yeah, so if we try to model this grid side converter, so here we need to know some models of these power converters. So here, if we take a look at these grid side converters, and we could see that if we use a single inductor as a filter, now here we can see that we can see some current in terms of the DC side, AC side, and the DC side. So here, if we by using the introduce the concept of this switching function, that means this S is defined that if this up switch is on, then this S will become 1, and if this lower switch is on, then this S will become 0. And here, if we by using this defining this switching function, now we can easily to know the outputs of this inverter voltage in terms of this DC link voltage. So here, if we try to try to adapt this KVL in this AC side of this generator, now we can try to find out the voltage in this loop and also across to this loop. So here we can simply write the voltage equations in terms of this way, and simultaneously, if we take a look at the DC side, now we can use this KCL law. Now here we can see that actually the DC link voltage will be the sum from this 3 AC side. Then we combine with this switching function and also the information of the loading current. Then we can deduce equations in this way. So here is basically the mathematical modeling of this grid side converter under this ABC reference frame. And if we know that in case of these three-phase systems, we know that the line voltages of this three-phase current will be always 0. And if this is balanced, and we can see that the grid voltage will also become 0 in terms of the three-phase system. Now we can do some simplifications, and we can write these equations in terms of this way. And here we can see that the inductor, the voltages across this inductor can be expressed in terms of the AC side and the DC side, and for the currents through these capacitors, we can also try to express the equations in this way. But the problem for this mathematical equation is that we can see that these equations are a little bit complicated, and they are also coupled with each other. So it's not easy to do this modeling. And another thing is that due to the concept of these switching functions, so this model is actually become discontinuous and non-linear. And in this case, this kind of the model is we cannot directly use that to do this classical controller design like this bot plot or this root locus analysis, etc. So that's why we try to introduce state average modelings. That means if we want to have a continuous modeling of the system, then we need to do switching averages. That means these every items under this ABC frame will do switching averages. So this value will become a mean value within switching periods. And here we can see that if we use this concept, we can change these switching functions to this duty cycle. And here we could rewrite the equations in the previous slide in this way. And here, if we try to take a look at this equation again, and here we can see that this system will become continuous and also linear. And the difference between this model and the previous model is that in these models, these switching ripples are not considered in this case. And then we can do some more simplifications of this three-phase system into the two-phase. And here we need to use some transformations before we can do this change. So first is that we call it Clark transformations. So in this way, we try to change this three static reference into this two-phase static reference. And the reference frame of this ABC and alpha beta actually can be seen in this figure. And here you can see that if we try to change from this ABC frame to the alpha beta frame, then we need to use these equations to do these transformations. And here you can see that if we that means we can simply try to mapping the ABC values under this ABC frame into the alpha and beta by do some projection of these values. Now we can actually reduce functions in this way. And if we want to do the way back, that means if we want to change back from the alpha beta to ABC, then we need to use these metrics that we can do these transformations. And here is the Clark's transformation. And moreover, we can use these Park transformations that we can try to change from this two static reference frame to this two-phase rotating system. So here, if we see from this picture, that means compare with alpha beta, the DQ reference frame is actually rotating with this omega. So here, if we want to change from this alpha beta to DQ reference frame, then we need to use these equations to do these transformations. And similarly, if we want to change back from the DQ to alpha beta, then we can use these equations to do the transformation. And here is another concept we need to know is that the space factors, because normally we know that in case of these three-phase systems, ABC reference ABC the values under this phase A, phase B, phase C are actually lagging 120 degrees. And if we try to combine these three scatters into one factors, then we need to use these space factors by introducing this factor of this gamma. And here, if we by using this concept, we can simply change this ABC in this three scatter system to this DQ frame. So here we can see that in case of this DQ frame, these AC components will become DC values, and also the three-phase system will become two-phase system. And the main advantage of this transformation is that since the AC values becomes DC values, so we can simply use some PI controllers to achieve this zero error tracking of these DC values. So it will make this controller design more easier from this perspective. Then we can try to do some transformations from this ABC frame to the alpha beta frame, and then to the DQ frame. And here in this DQ frame, we can see that actually the system will not become fully decoupled, because we can see that this D-axis value is actually also related to this Q-axis currents. But this system is very simple compared to the previous version, and this model is continuous. So we can try to use the classical controller design to design this PI controller, for example. Yeah, then these previous models we mentioned is actually this large signal modeling. That means it's this it's a large signal, and if we try to do a more small signals analysis, then here we can see that these values will become actually the DC components plus these disturbance values. And then by using these equations, we could actually know the equations under this static operation, and also we know the equation under this disturbance. And here in this case, we could use this as a model or the control plant of this system, and later on we can try to design these controllers based on these equations. So if we take a look at the control structures for these gray side converters, so here we can see that actually we have this dual loop structure, and the inner structure is normally the grid currents, and the outer structure could be DC link voltage or this electric power. And normally, if we want to don't have the conflict between these dual loop controllers, so the bandwidth of these two systems will be far away from each other. So by now we can, if this bandwidth can be achieved in this criteria, then we can try to develop this controller design step by step. So here we will try to design this controller from the inner loop first, and then we will develop this outer DC link voltage loop. Yeah, so as we mentioned before, if we know this small signal modelings of this system, then actually we can know the analytical equations for this control plant. And if we draw this plant in terms of this figure, and here we can see that actually this plant of this grid current will be expressed in this way. And here we can see that this system is not fully decoupled, because some items, for example, the D-axis currents will have some impact on the Q-axis currents. And in order to cancel out this kind of the impact, so here we try to use some decoupling control in case of this controller design. And if we try to use these crossing items, then we can try to eliminate the impact from the decoupling. And then this control plant will become much easier in terms of this linear system. And another thing is that if we use this PWM, and normally some control PWM delays will be introduced in case of this modulation period. So here, generally speaking, we have two kind of sampling system. One is that this we call it symmetrical PWM. That means only one values will sample within one switching frequency. And here we can see that in case of that, we will see that the delay will become 1.25 of the switching period, because this kind of the delay is actually consists of the two parts. The first part is the sampling delay, and here is one switching period. And the second part is this PWM delay. And here you can see that the minimum will become 0 and the maximum will become half of the switching period. So here we do an average. Then here we can see that a quarter of this switching period will be contribute to the PWM delay. So if we add these two items together, now here we can see that actually the delay for the PWM will become 1.25 switching periods. And we also have another modulation techniques is that we try to use this asymmetrical PWM. And here in this case, we can see that two values will be sampled at one switching frequency. That means at the bottom or as top value of this carrier. So both value will be censored. And here in this case, we can see that the sample delay will become reduced to a half of this switching frequency. So here we can see that the total delay of this PWM will also become lower compared to this case. And in case of this modeling, even though this PWM delay is purely delay unit, but normally this time period for this delay is very slow. So here we can just use as an inertial unit, try to model this PWM delay. And then if we have this plant of this grid filter, and if we also have the PWM delay units, and together with our PI controller, then we can try to draw the control block diagram of this current loop. So here we can see that for the control plant is a linear system, and for the PWM units is inertial units, and we can also write out the transfer functions of this PI controller. And here in this way we can simply calculate the open loop transfer function of this grid current, will be the product of these three subsystems. And then the design criteria of this inner current loop is that first of all, in order to eliminate this switching ripples, so here we try to have the bandwidth of this inner loop between 1/20th or 1/10th of this switching frequency. And another thing is that we also need to have enough phase margin to avoid this instability system, because here we could see that if the phase margin becomes 0, then the system will become this positive feedback system. So the system will become unstable. So here normally we try to have this phase margin over 45 degrees. And once we have this design criteria ready for this PI controller, and here we try to design two Dfid system. One is a real megawatt system, like 2 megawatts that exists in the wind market. And another thing is that in order to validate this design in our experiment prototype, we also have a downscaled Dfid system that is rated with 7.5 kilowatts. So if we know the parameters of these two kind of the system, then we can see how we can design these PI controllers step by step. Yeah, so first of all is that if we take a look at the dot plot in terms of the magnitude and the phase, and here you can see that the plant is a solid line in this phase because it's a pure inductor. And now we can see that normally the dot plot for this PI controller will be this kind of curve. So here we can see that if we want to have the different bandwidth of the system, we could simply change the proportional value of this PI, try to move this plant of this open loop transfer function to the up or the lower side of this figure. And here then we could try to design this bandwidth as 100 Hertz. That is only 1/20th of this switching frequency, which is 2 kilohertz. And by using this design, we can see that actually, if we take a look at the surface margin, and it's also higher than 45 degrees. So here is around 60 degrees in our design. And in order to verify the robustness of this controller, and here we also try to use the different filter inductance values. For example, if this inductance is become the value of the 2 times higher compared to before, then we can see that actually the bandwidth will become a little bit lower, but we can see that we still have the enough phase margin to have this system stable. Yeah, so this is the way we can design this bot plot for this 2 megawatt system. And similarly, if we take a look at this 7 kilowatt system, we can also try to design this bandwidth within the switching frequency. And here we can also try to keep this phase margin higher than 45 degrees. So this is our cases here. And once we have this inner current design ready, then we can move forward to this outside. So if we take a look at the equations from this DC side current, then we could know this equation. And if we do some negatifications of this Q access current, then simply we can deduce the plant of this DC capacitors is in kind of this also this linear function. And this, once we know this control plant, and if we know, because previously we designed this open loop current loop, and if we try to have this loop closed, then we will have the transfer functions from the reference to the real value. And by adding this voltage controller, here is still a PI controller, then we can know what is open loop transfer function of this DC link capacitor voltage. And similarly, we can see that for the controller is PI parameters, and for this closed current loop, we can deduce that from the open loop transfer function from this grid current. And this is the plant for this DC capacitor. And finally, if we know this filter capacitor, some filtering units for this DC link voltage, then we can draw open loop functions in this way. Yeah, so the design criteria is that similar as before, is that we need to avoid some interactions between the inner loop and the outer loop. So here we try to have this bandwidth of the outer loop at least 1/10 of this inner loop, and at the same time we need to keep the phase margin higher than 45 degrees. And these are some parameters we use for this two system. And now we can, if we take a look at this 2 megawatt system, so here we can see that in case of the bandwidth, we can see that the bandwidth of this voltage loop is only 1/20 of this inner loop. And if we take a look at the phase margin here, we also have the planting of the degree. Here we have this around 80 degree for this phase margin. And similarly, we can see the case for this 7.5 kilowatt system. So here you can see that the bandwidth is also far away from this inner current loop to realize fully decoupled. And in terms of the phase margin, is also fulfill this criteria. And then we can, if we have this design PI parameters ready, then we can draw this control scheme of this grid side power converter. So here we can see that first of all, we need to use some PLL to know what to do the DQ transformations. And now with these PI parameters ready, now we can use these PI parameters in this inner current loop and outer voltage loop to have this control ready. And here we can try to see what's the impacts of these controllers if we do some simulation results. So first of all is that we try to do some simulation at this 2 megawatt system, and we can have a step change in case of this Q access current, or in case of this DC link voltage, now we can actually see what is step response time for this inner current loop and outer voltage loop. And here, as the same case, the difference is that we only consider that the grid filter impedance will become two times higher compared to the original value to see the robustness of this system. So here we can see that in case of the step change, we can see that this voltage reference and this current reference is well checked by the actual value. Yeah, and now we can do some experimental validations in a downscale system. So here we can see that for this 7.5 kilowatt system, this wind turbine is emulated by a prime motor. So that means the generator is driven by another prime drive in advance. And here we use some Danfoss power converter that can be consist of this back-to-back power converter. And here we use the control system as a DSpace, which is very easily linked to these Simulink simulations. Now we can try to measure what is the stator current and what is the load side current for the control of this load side converter, and we can also try to measure the grid voltage and the grid current to see what is the control performance of this grid side converter. And here we can see that because previously we only try to design this bandwidth in terms of the bandwidth of phase margin, and how we can try to link this bandwidth in terms of this time domain information, like the step response time, etc. Because so here, since this system can be roughly considered as a one-order system, so we could basically know that there are some certain relationship with the bandwidth and this rising period. So here, by using these equations, we could know that if the bandwidth for this 7.5 kilowatt system is 300 hertz or 10 hertz, then we could simply calculate what is the expected rise time of this bandwidth. And now we can do a step response in case of the grid current. And here we can see that actually the step response is 1 millisecond. That is very close to the expected raise time. And similarly, we can do a DC link voltage step response. And here we could actually also measure that actually this response time is very similar to the design bandwidth we designed before. So here in this way, you can see that this bandwidth and the rise time are actually well agreed with each other. That means the controller designs is well verified by using this step response method to verify. Yeah, and previous is something on this controls based on the DQ reference frame. So we need to use a PI controller. And at the similar time, if we want to control these signals on the alpha beta reference frame, then we could actually use this PR controller. And here we can see that actually the PR controller is very similar to this PI controller, besides a phase shift for this integral coefficients. So here, if we try to combine these equations together, we can see that actually this PR controller is also consists of this proportion factor and also these resonant factors. But this ideal PR controller is very sensitive to the grid voltage variations. And here, in a case of the critical PR controller, and we need to insert some resonant bandwidth for this controller, then it will become less sensitive to the grid voltage. So here we can see that actually these are some gains for this proportional and the resonant, and here omega 0 means the grid frequency, and we can also try to use different resonant bandwidth. to make this PR controller less sensitive. Yeah, so if we take a look at the open loop transfer functions for this grid side converter control, and similarly, you can see that there's a delay unit. It can be controlled as a delay unit, and the control plant will be this inductor, and this PR controller will in these terms. Now we can also write the open loop transfer function for this PR controller design. And here we can see that, as we mentioned before, for this PI or PR controller design in this bot plot, we need to fulfill two requirements. One is this bandwidth, and the other one is the phase margin. But if we talk about this PR controller, there are one more criteria we need to consider, is that even in case of this resonant frequency, we also need to have enough margin to make the system stable. So here we have two cases to show how we can design these PR parameters. So the first case is that if we have the same phase margin at this cutoff frequency, 45 degree, and we could have the different phase margin at this resonant frequency, either as 45 or 60. So here we can see that in case of, because here we have the same bandwidth, so here we can see that the proportional values of this controller are the same. But if we talk about this resonant coefficient, then it will become a little bit different compared to each other if we want to have the different phase margin at this resonant frequency. And similarly, if we want to have the same phase margin at this resonant frequency, but now we will result in the different bandwidth and also the phase margin at the cutoff frequency for this system design. So here we could design some parameters based on these two conditions. And if we try to compare the results with the different phase margin at this cutoff frequency or this resonant frequency, then actually we can see that if we have the higher KP, then we will have the lower THD in this case. And also in terms of the response time, we can see that it will also be more quick to get this reference current in this case. And if we use the different, in case of the higher phase margin or higher lower bandwidth, then here you can see that actually the THD will also become a little bit higher compared to the previously condition. Yeah. Then these are all about modeling and control for the grid side converters. And if we try to move forward to this machine side converter, then we need to divide them into two kinds. One is the Dfid, and the other one is the PMSD. So first, let's start with this modeling of the Dfid. So this is a typical model of this Dfid under DQ reference frame. So here we can see that based on these two models, we can simply know the voltage equations and the flux equations for this under this DQ reference frame. And now we can deduce the modeling of this Dfid based on these two equations. So first is that if we try to use this state voltage oriented control, then we can see that the Q-axis of this voltage will become 0. And during the steady state, if we try to neglect this state resistor, then we can actually calculate the steady state values for the state flux in terms of the D and Q axis. And then based on these equations, we could know that the state side current is actually can be represented by the load side current. And if we know this equation, then we can express this load flux in terms of the load current. And moreover, we could deduce the load voltage in terms of this load current. And if we know these equations, then it can be actually considered this control plant of this load currents. And moreover, if we know this equation, and we can also try to calculate the active power and the ready power in case of the state side by using this load side information to calculate. Now, if we know these two equations, now we could actually know what is the inner loop and the outer loop control plant for this DFIG. Yeah. So if we take a look, yeah. So here is actually the control plant that is deduced at the previously mentioned equations. So here, if we consider the input is the load voltage and the output is the load current, so this is actually the control plant for this load current. And similarly, if we know this load current, and we can also deduce the active power and reactive power of the state side by using some equations. And here, if we know this analytical equations in between, then we can actually calculate what is plant of this active and reactive power. So then, if we know this control plant of this system, and then we know that normally for this control of the machine side converter, normally we also use this dual loop system. And inner loop is load current we do control, and the outer loop could be the power or the speed if we like. So then we can follow the similar procedures in case of this grid side converter. Then we try to design this inner load current loop first, and then once it's ready, we can use this information and try to design this outer power or speed loop based on the inner current information. Yeah. So here we need to keep in mind that there are a slightly difference between the previously mentioned equations, because for the DFID models, normally these load side values are referred to the state side, and if we try to change back from the state side to the load side, then we could need to use some equations that we do need to do some transformation. And if we take these two factors into this plant of this load current, now we will try to have this control plant transfer functions ready. And if we know the PI parameters of this PI controller, and then we can know what is the open loop transfer functions of this system. And here again we list some key parameters for this 2 megawatt and 7.5 kilowatt system. And if we know this system, now we could simply draw what is open loop transfer function for the load currents. And here we can see that for DFIG model is still a kind of the linear system. So it can be seen that there is a turning point here, and afterwards we are in terms of the minus 20 dB per decade in terms of this way. And if we try to design this PI controller, then we can move these plants up and down and to reach our desired bandwidth. So here is 100 hertz in our case. And once we have these PI parameters ready, and we can also see the phase margin from this phase diagram. And here we can see that for the phase margin here, we have more than 60. So it's enough for the system stability. And here, if we also consider the robustness, that means if the mutual inductance is reduced to half, then here we can see that actually this parameters is not that sensitive, because we can see there are not so much changes in case of this dot plot diagram. And similarly, we can use the same design method for this downscale 7.5 kilowatts. And I will not go into details about the bandwidth and the phase margin here. Yeah, so once this inner loop inner loop of the load current control is ready, then we can try to have this as a closed loop function by use this transfer function. And then if we know the plant of this red power, we give it take it as an example. Now we can use these three sub items to draw this bot plot for this open loop transfer function. And here again, we can see that if the inner loop is 100 Hertz, then we can design this outer loop as a 5 Hertz. And here we can see that the phase margin is also enough for this outer loop. And the similar case is happens for the 7.5 system. And we can see that, yeah, we have enough margin from the inner loop and the outer loop bandwidth. And we also have enough phase margin for this case. And again, if we try to use that parameters into the simulation, then we need to know the control scheme of this machine side converter control. And here we can see that besides the PLL of the stator side voltage, we also need to measure the load speed to know what is electrical angle of this machine. And then we can do some DQ transformations based on these two informations. And once it's carried out, then we can try to do some step response in case of the D-axis load voltage and also the out loop in terms of this reactive power step response. Now here you can see that actually this, regardless of the current or the power, actually I can well check these reference values quite well. And then similarly, we can do some experiments in this case. And here you can see that in case of this step response for the current, and we could calculate what is the rising time, and we can check whether this rising time is according to our design bandwidth. And similarly, here we could also do a step change of this reactive power. And here we could also try to measure what is the rise time of this outer loop. Now we could see what whether this control bandwidth is well designed or not. Yeah, so these are some control strategies based on this factor control, and we can also use some other controls like this directly power control. So what is the difference between this active direct control and the factor control? Because as we mentioned before, for the factor control, we need to use this dual loop system, inner current and outer active power or reactive power, these things. But here, if we try to model this, we try to use this direct power control, and actually this load voltage can be directly expressed in terms of the active power or reactive power from the stator side instead of this load current. And by using this way, we need to use one loop instead of the two loop to do the control dual loop structure. So here if we take a look at this modeling for the low side converter. So here we can see that if we use this power loop power as a reference, then here we can directly use power as a feedback. Then we can only use this single loop system to achieve this direct power control. And similarly, we can also try to divide this grid side converter's voltage that can be expressed from the grid side active power and reactive power. And here we can also use these single loop structures in terms of the power instead of the grid side current to do this direct power control. And here we have some parameters for this system. And here we could see that we show some steady state operations in terms of the low side converter and the grid side converter. And in case of the low side converter, we can see that the state voltage and current is actually out of phase. That means it's working at this unity power factor. And here we can also see that the load current has a much lower frequency compared to the stator side, because it's only the slip frequency compared to this stator side. And similarly, we can see that for the grid side converter, we can control this DC link voltage as a fixed value. And the grid current is also well checked this reference. Yeah, so these are some modeling for this Dfid induction generators. And if we try to talk about something on this PMSG, and then we need to do the different modeling, especially for the machine part, could be different from the Dfid system. And here, if we try to take a look at this steady state equivalent circuit for this PMSG, then we can see that it can be actually divided into the DQ reference frame, and the equations and the equivalent circuit under the D and Q axis is actually in this way. And here we could still see that there are some coupling atoms, which is a D and Q reference frame. As Q access current will have some influence on this D access voltage. So if we try to draw this DQ circuit in terms of this control plant version, and here we could again see that actually some DQ coupling effects exist in this model. And then if we try to eliminate this coupling effects, then we can try to choose some items, controls cross items in beforehand to try to cancel out the coupling effects in this model. And here, if we use this stator side current as the inner loop and the outer loop as a speed, then we could again have these dual loop structures to do the PI controller designs, etc. But here we will not go to the details for this PI controller design, because there are some similar process when we do this Dfid system. So with these key parameters from this machine side converter and the grid side converter, we can do some simulations for this back-to-back power converter of the PMSG system. And here we can see that for the grid side converter, we can see that actually here is grid voltage and the grid current are actually in phase or out of phase. That means we have the unity power factor, and we can also see that the DC link voltage is well kept as a constant value. And if we take a look at this machine side of this converter design, and here we can see that actually we can control this rotor speed at constant, and the active power and reactive power is also works as desired, and we will also have the constant D and Q access state current at the steady state operation. Yeah. So to summarize what we have done in this part is that we first take a look at this control targets for this Dfid and the PMSG back-to-back power converter. And for the grid side converters, we can see that we go through the detailed process, how we can do some modeling and control of this inner grid current and outer DC link voltage. And if we want to design this controller under this DQ frame, then we can use the PI controller. And if we want to control this system under the alpha beta system, then we could use the PI controller. And the design process of these two controllers could be relatively the same compared to each other. And if we talk about these machine side converters, then we need to divide them into the two parts because the model of the DFIG and the PMSG is different. And for the DFIG system, we go through the controller design procedures of this PI controller in terms of the inner rotor current and also the outer stator power. And we also introduce a bit if we want to use this direct power control instead of the factor control, then we also show how we can model and how we can control these systems if we use this direct power control. And finally is that we also talk about this PMSD system, and we do some control modeling of this machine and also some simulations to verify whether this machine side converter can be well controlled. Yeah, so this is the part of this control, factor control in terms of the PI controller. Any questions for this part right now?
Maybe just a technical question. Can you share the presentation with us?
Sure.
Okay.
Yeah,
I think it's worth to have another look at it.
Yeah, we'll share it afterwards.
Thank you.
Okay, then if no more question, I suggest we have a 10 minutes break, and afterwards we will continue with this fourth rise-through operation of this Type 3 and Type 4 wind turbines. Yeah, see you later. Okay, now the time is 3:25, so I think we continue again. Yeah, so for the third part, we will try to cover what is abnormal operation of this wind turbine system. So first of all, we will begin with these classifications of the grid faults, like what is symmetrical grid faults and what are asymmetrical grid faults. Then we will mainly focus on this DFIG and the PMSG system and try to see how these two systems will affect under this different kind of the grid fault system. Yeah, so first of all is that a definition of these grid faults. So first of all, if we take a look at this general configuration of this wind turbine or wind farm system, then here you can see that at the turbine cell, we have this step-up transformer, try to change from this low voltage to medium voltage. And in between, we have a central transformer. That means we need to transfer from this medium voltage to high voltage. And here, normally, we need to have these YD transformers in between in this case. And here, if we can see that if it's a fault that happens in close to PCC, and then we first of all we need to have a definition of this dip level. So what does this dip level means? So this dip level is that is a value between 0 and 1. If this dip level is 1, then that means the voltage will become 0. And on the opposite, if this dip level is 0, then we can assume that this grid voltage is normal. So actually, the dip level of this grid force is actually mainly related to how far away this force is how far away this force is away from this PCC. So here we can see that if this impedance of this force is 0, now we could see that actually this PCC voltage will become 0 at this case. So in this way, we can actually, by using this impedance from the grid and to the force sort, and then we can try to define this dip level is actually the value between this impedance of the grid over the sum of the impedance of the grid and for the faults. Now here we could use this dip level between 0 to 1 to define how severe this grid faults is happening. Yeah, so for these fault types, generally speaking, we know that it can be divided into two parts. One is this symmetrical grid faults, and we can call it three-phase grid faults. And we also have some asymmetrical grid faults like single-phase and line-to-line phase and two-phase to ground. This kind of different types. And here we can see that actually the fault happens at these conditions. And if the force is transferred to the wind turbine, then it will come across this YD transformers. And here, during this propagation of this grid faults, there could be some changes because we know that for these delta transformers, the 0 sequence cannot be passed through this transformer. So there could be some propagation issues in terms of these grid faults. And here we can see that if we say this fault type in PCC, we have 4 types. One case of this symmetrical and another 3 cases of this asymmetrical. And if we try to see that from this phasor diagram, and here you can see that in case of the 3-phase force, then it will be type A. The phasor diagram will be seen in this way. And in case of this single faults, and here we can see that actually one phase will become lower, and here we can see that the phasor diagram will look like in this way. And in case of this line-to-line failure, and we can see that the phasor diagram will be in this way. And for this two-phase to ground faults, now here we can see 2-phase of the voltage will become lower, and it will be expressed in terms of this way. And however, if we take into account of this YD transformer, so there could be some distortions if we go through this transformer. And here we can see, generally you can see that for the three-phase faults, the phasor diagram will be the same. But in case of the single symmetrical grid faults, we can see that these configurations will, or this phasor diagram will be slightly different from each other. And the key conclusion is that we can see that in case of these symmetrical grid faults, some may have these zero components. But this zero sequence component cannot be presented after this YD transformer. So here you can see that after this YD transformer, this zero sequence will all become zero. And in case of this positive sequence, they all will remain be the same, regardless of this transformer function types. But in case of this negative component, we can see that the value will become the opposite value. So once we know these values, then we will actually know what is the type from these six figures to see which is corresponding to which kind of the fault type. If these are some propagation issues of the grid faults, we need to take into account. Yeah, so for this grid code requirements for this low voltage rise through, and as we already mentioned before, that if we encounter a different level of these grid faults, maybe it's a different withstand time is required, and that are basically dedicated to this balanced grid faults. And in case of this symmetrical grid faults, like two-phase faults, there are some different requirements. In this case, here is it's a code from the Danish code, grid code. And similarly, we can see that if we also need to absorb or inject some red power in case of the different voltage, in case of the different voltage levels. And now we can first take a look at how this Dfid will react in case of the grid faults. And the challenges for this Dfid to rise through this fault operation is that, as we mentioned before, that since the data of this Dfid is directly connected to the power grid, and in case of the grid fault happens, a state flux cannot be changed immediately. And here, if we take a look at this deductions of this load voltage. So here we can see that the load voltage can be expressed in terms of this derivative of this state flux. And if we change this state flux back to this load reference frame, then it can be expressed in this way. And here, if we take a look at the models, we can divide into, in case of the grid fault, is that we know that since state flux will consist of the positive components and the natural components, and also the negative components. So here, in terms of the machine, it can also be divided into three types. And for the positive machine, we can see that the EMR that is in the loader side is only almost the product of this in related to this state value. But in case of this natural machine, we can see that since the rotation speed in terms of the loader speed is changed, so here this value will be in relation to this 1 minus this state value. And here we can see that since the state value is normally close to 0, so we can see that in case of this natural flux, this EMF caused by the loader side will become much higher compared to the normal conditions. And in case of this negative machine, and we can see that actually the loader voltage will become much higher, because this value will be in relationship to this 2 minus this state value. And here we can see if we have some negative components of the state voltage, now we can see that it caused the EMF will become much higher at the loader side. So in this way, we could see that in case of this grid force, the loader side voltage will become much higher, and this will exceed the control range of the DC link voltage, and it will cause out of the control of this load side converter. So this previously we mentioned some cases for the balanced or symmetrical faults. And here we can see that the maximum and the natural state flux will be the same for the symmetrical grid faults. And in case of the asymmetrical grid faults, we can see that the previously chase of this state flux is a circle, and the final one will become this ellipse. And depending on the fault time instance of this fault appearance, then the maximum and the minimum natural flux could be different. So for the single phase, we can see that if the fault happens at this condition, now we can see that it will induce up to 1 over P dip over 3, this value of this maximum state flux. And if this fault instance, for example, is happened at here, then we could see that the minimum natural flux will become 0. And similarly, we can see the case for these line-to-line voltages. And depending on the faults happening time, the time instance of these faults, then it can also depend on we can determine what is the maximum and what is the minimum natural flux that will be introduced as the different asymmetrical grid faults. In order to overcome the issues of this nature flux, there are some state-of-the-art solutions that can help this load side converter to overcome this issue, and it can be divided into two parts. First is this hardware solution, and the second one is a software solution. And in terms of the hardware solutions, can be realized by this DVR. We call this dynamic voltage restorer. And what is the function of this DVR is that in case of the grid faults, then this DVR can provide some voltages that can keep this state of voltage as pre-fault conditions. And here in this way, we could keep that natural flux out of the range. And this is one case. And the other case is that we can use this crowbar either in the DC side, AC side, or in the DC side. And the function of this crowbar is that it will try to accelerate the damping of the natural flux as soon as possible. And once this damping is done, then the system will go back to the normal conditions and could be under control again. And these are the hardware solutions we could see. And alternatively, we can also use some software solutions like demagnetizing control. And we will talk about this later in detail for this kind of control scheme. Yeah, so the concept of this demagnetizing control is that we try to control this loader current that is in the opposite direction of this nature flux. And in this way, all capabilities of this loader current will be used to overcome this transient nature flux. And if we take a look at this phasor diagram for this loader voltage and current, here we can see that if we try to control this loader current in the opposite directions of the nature flux, so the voltage across this transient resistor and inductor of the load side will be on the opposite directions of this ESR. And then if we try to change that, then it will try to bring this loader voltage back to the control range. And it will help us to counteract this loader EMF if we use this demagnetic control. Yes, so here we can see that in case of the symmetrical grid faults, and if we take into account of the different rotation speed, And here we can see that basically we can see that the higher speed of this rotor speed, we could see that the EMF will become higher due to this original rotational speed. And here, if we try to use some demagnetizing currents, then here we can actually try to reduce this load voltage and try to bring these converters back to this safe operation area. And here we can see that actually higher demagnetizing current we use, and we can have the higher safe operation areas of the load side converters. And here we can see that in case of this, if we use 2 per unit demagnetizing currents, and here you can see that in case of the low speed, we can rise through all fault levels, even the diff level is up to 1. And in case of if the load speed is higher, and if we take it into a case for this 1800 RPM, so here we can see that if we inject this 2 per unit demagnetizing current, but the dip level you can withstand is only in less than 0.7 in this case. But if we compare with lower demagnetizing currents, here we can see that actually the rise-through capability will even become lower if we use the lower amount of these demagnetizing currents. Yeah. So if we take a look at the control scheme of this DFIG under this symmetrical grid force, so here we can see that in case of these normal conditions, we normally will control this active power and reactive power. And in case of this fault occurrence or this occurrence, then here first we can use some observers to know what are the natural components of this state flux, and also what is the demagnetizing coefficient we need to use to achieve this 2 per unit demagnetizing currents. And here, if we know that the fault happens, then we first of all is that we need to inject some demagnetizing current to keep this converter under control. And second is that we also need to inject some reactive power that can be support the recovery of this grid voltage. And moreover, we also need to bear in mind that not only in case of the fault occurrence, but also in case of the fault occurrence, we also will introduce this demagnetizing current. And so at the very beginning, we also use this demagnetizing current to try to reduce this natural flux as soon as possible. And after a certain time of the period, then we will switch back to this factor control of the active power and reactive power. So here we have a simulation comparisons of this DFIG system at this 1800 RPM rotor speed. And on the left is we use the normal factor control, and on the right is that we try to use some demagnetizing control. And here we can see that if we use the traditional factor control, we can see that under these fault conditions, actually this real load current is not fully follows the reference of the load current. This is one point. And on the other point, you can see that the state flux is actually damping very slow, and it can be superposed in case of the voltage recovery. And we can see that there are also a lot of fluctuations in case of the DC voltage. And if we use the demagnetizing control, and here you can see that in case of the grid force, we can see that actually this load current is follow this reference quite well. And meanwhile, we can see that this natural component is damping much faster compared to the normal factor control. And yeah, and in case of the desync voltage, we can see that it will also be much more smooth compared to these factor control conditions. So here we can see that the demagnetizing control is much better compared to this factor control if we have some symmetrical grid fault happens. And for the different case of these asymmetrical faults, so here we can say that if we take into account of the different types of these asymmetrical faults, we can see that the fault rise-through capabilities of this system could be different, and it's less than 0.5 for the best case, and inspired by this demagnetizing control under this symmetrical force, we can also use some method that is applicable to these asymmetrical faults. So here we can see that before if we do some positive component control of this Dfid, then we can see that actually this load current is actually in the opposite directions of the state current. And here we can try to control the active power and reactive power in this way. But if we use the demagnetizing control, that means if we try to consider the negative components of this state flux, then here we can see that actually this load voltage or load current will be the opposite directions of this negative state flux. And here in this we can see that it will not control the active power, but it will in case control this reactive power in this case compared to before. So if we still try to use this 2 per unit demagnetizing currents, and here we can see that this fault rise-through capabilities will be much more improved if we use this demagnetizing control. So here, for example, in case of this single phase faults, we can see that the Dfid can ride through up to 0.8 dip levels. So its previous is only like 0.44 in this case. And similarly, in case of this line-to-line phase or two-phase to ground faults, we could also try to increase this fault rise-through capability quite a lot by using this demagnetizing control. And here we can take a look at the state diagram, control diagram for this Dfid control under this symmetrical grid faults. So here we can see that during the normal operations, we will try to control this active power and reactive power under this case. And in case of the faults rise-through, first of all, we need to control this load current on the opposite directions of this negative state flux. And this kind of the informations can be calculated by this flux observer and also some notch filters to try to decompose it, the negative, positive components here. And now we can also try to control this current in terms of the positive and negative sequence. Then we can try to see what the state current and the load current behaves in this case. And here we also do comparisons between this factor control and the demagnetizing control. And here we can see that in case of this single phase grid faults, we can see that the reference current of the load side cannot be is not well checked by this feedback current, and they are and if we take a look at the load side current, they are not ideal as well. And if we try to take a look at this demagnetizing control, and here you can see that in case of this grid fault, these two currents in case of the d-axis and q-axis, and also in terms of the positive and negative component, they are well controlled. And once the grid faults go back to the normal, And here you can see that these informations can be, or this reference can be well checked as well. Yeah, so here you can see that actually the magnetic control is much more preferred in case of these asymmetrical grid faults. And then we can talk about these type 4 wind turbines, which can also overcome these different grid faults. So here, different from this DFIG system, because for the DFIG system, it's actually mainly loader side converters, which is those overcoming techniques for these grid faults. But here, because we know that the generator and the grid is fully decoupled by these back-to-back power converters, so actually here the grid side converter will be the key performance that will handle the grid faults for the different type of the grid faults. So here, we could see that this is a general control structures during the grid faults. And here we can see that we have this outer loop teething voltage and the inner loop grid current. And we also use PLL structures, try to measure this PLL information. And by knowing this control plant, we can, by using this control scheme, we could know the control plant for this LCL filter. And this actually is use this PR controller, because this system is controlled under this alpha beta frame. And by also knowing the parameters or the transfer functions of this PIR controller, then we could deduce the current open loop transfer functions in terms of this equation. And by knowing these key parameters or the reference of this 7.5 kilowatt system, now we could actually do a symmetrical grid faults. And here you can see that if the grid voltage is become a half of the previous value, now we can see that during this grid fault, this D axis and Q axis current is well checked this reference at the beginning. And once this grid voltage is go back to normal, and here you can see that the Q axis will become 0 again. And the D-axis will become higher because it will try to provide the active power as before. And here we also consider a severe condition that in case of the zero voltage rise through, and in case of the zero voltages, the PLL, for normal PLL will not be working because there are not any phase angles or the amplitude it can be predicted from this normal PLL. So here we try to use these adaptive voltage nominations to in case that the grid voltage is changing, then here the output from the PLL will be different. So here generally is freezing model is performed in this way. So we have this threshold voltages. So if this PCC is higher than this threshold voltage, so this PCC is working as normal conditions. And in case that the PCC voltage is too low, then we try to freeze these voltage informations and try to give the phase angles based on the pre-fault information. And in this way, we could know the grid voltage and the grid angles even under this zero voltage condition. And once the fault is cleared, then the PL will switch back to these normal conditions again by use this threshold voltage information. And here we can do a comparison of this zero voltage rise through operation in case of having this freezing method or without this freezing method. So here we could see that in case of this zero voltage rise through, if we don't use this freezing method, then we can see that the frequency of this grid cannot be acquired anymore. So it will cause some unstable operations of this system. And here, if we use this freezing method, then we can see that even under this zero voltage right through, we still know the PLL informations like the frequency of the grid. Then in this way, we could provide the required current as we need it. And once this voltage is back to normal, then the converters can switch back again to this active power and reactive power control as in the previous condition. Yeah, now we also need to use some PLL to know the positive and negative sequence of the grid. And compared to this different kind of PLL can be used. For example, we can use soggy PLL or kind of the other PLL. And here in this case, we use this phase shift of this PLL. So first of all is that we try to use this phase shift to acquire the positive components of this grid voltage. And if we use this another additional units, then here we could actually try to extract not only the positive component, but maybe also some harmonic components by using this unit. And so here, before we do the SRFPLL, now we first try to extract the positive components of this grid voltage. And now we can use this information to the normal PLL to try to extract the positive and negative components of the grid voltage. And here, once we know the positive and negative components of the grid voltage, and based on this active power and reactive power required by the grid codes, then we could use different current reference in terms of the positive and negative. And here we can see that if we take a look at this phasor diagram, we could see that in terms of the positive sequence current, it will be kind of this counterclockwise direction. And if we talk about this negative sequence current, then this current will work as these clockwise directions. So if we try to combine these two trajectories together, then this kind of this circle will become this ellipse. So here we could, based on the requirements of this positive or negative components of this grid current, then we can try to produce a different shape of this ellipse to fulfill the requirement from the grid code. Yeah, so this is the control structure of this grid side of this BMSG that is subject to this asymmetrical grid faults. So here we can see that we have this outer voltage loop control and inner current control, and here we can do some sequence selections for the positive or the negative components of the grid current. And here we have comparisons that we try to use if this grid side converter is subject to this single line grid faults or this line-to-line grid faults. And we also do comparisons with this basically balanced positive signals control and also this flexible positive and negative component control in this scheme. And here you can see that regardless of these different fault type, we could see that these unbalanced factors will become lower if we use this FPNSC method. And also in terms of this fluctuation of these DC link voltages, and if we use this FPNSC control, then the fluctuation will also become slower. Yeah. To summarize this part, we try to investigate. First, we begin with the investigation of these various fault types, and we also consider this propagation of these grid faults if we take into account of these YD transformers. And now we talk about this Type 3 wind turbine to overcome these grid fault conditions. And challenges for Dfid is that since it will introduce this natural state flux that may lead the slow side converter out of control. So this is a key challenges we have here. So now we could use demagnetizing control to overcome this natural state flux as soon as possible. And in case of the asymmetrical grid faults, we also need to take into account of this negative state flux and try to control that in the opposite directions to have this lower EMF as small as possible. Yeah, so for this Type 4 wind turbine system, first, in case of this symmetrical grid faults, we use advanced PLL that can be used even in case of this zero fault is right through conditions. And for these asymmetrical grid faults, we will have some advanced reference generation methods that with dual sequence current provision. Yeah, so this all for this control part of this wind turbine system, and there are the contents of these slides are mainly come from this book. We call it the Control of Power Electronic Converters and System, and basically it's come from the following 3 chapters that is connect to this lecture. Yeah, so that's all